Okay, we're going to continue on here, obviously, with chapter 12, I think. So we've been talking about kinetics, and last time we really went over pretty much the whole time how to calculate the rate law, how to figure out the orders for the different reactants using experimental information, and then ultimately how to calculate the rate constant from that information. Again, the importance of doing that is essentially when you go to the table, you want to pick a couple entries where you got really everybody constant except for one reactant. And you could use that rate 2 over rate 1 sort of formula that we used last time to help you determine the orders. Once you do get the orders, then you could go back and solve the rate law for K. And to calculate the rate constant, you can choose, again, as we talked about, really any entry in the table. They all should give you the same value since it is a rate constant. So where we're going to move to now is to talk about a little bit more about specific types of reactions. So we also talked about sort of overall, there's reactions that are necessary first order, second order, and so forth. So the first type of reaction we're going to talk about is a first order reaction. And in a first order reaction, you really can achieve it sort of a couple different ways. The first way is we have A goes to products. In this case, the order for A is 1. That would be obviously one way that you could achieve it with one reactant. You could also achieve it if you had maybe 2 reactants where one of the orders was 0 order with respect to one of them and the other one was first order. That also would obviously give you a first order sort of reaction. So if we write sort of our rate expression for this guy like we did before and put it into our rate law here, we get the rate is equal to K, which is our rate constant, times concentration of A. Solving our rate law for K gives us one very important thing to remember for first order is the units associated with the rate constant for a first order reaction are 1 over seconds or reciprocal seconds. It doesn't necessarily always has to be seconds, but it is 1 over some unit of time. So, it could be minutes, it could be hours, days, whatever it may be. A lot of times we do obviously deal in sort of seconds in terms of our units. If we do in a reaction or experiment like we'll do next week, we're not going to probably sit there for days or anything like that. So we'll kind of time it for a certain amount of seconds. So seconds is a very common unit, but again, you shouldn't be sort of trapped with the units of seconds because there really can be any unit of time on the bottom there, but it is 1 over basically a unit of time or 1 over seconds. The importance of that is, as we will see in this couple of slides here and a few slides down the road, depending on the order of the reaction, there are different sort of equations or formulas that you need to use. And a lot of times in problems, they will not in flashing lights go, hey, this is first order, this is second order type of equation, but they will give you the value of the rate constant, and they expect you to know that just looking at the units from the rate constant, what type of order you're dealing with. So that's a really big hint that you do see, again, 1 over seconds. We're dealing with first order, which means if you're going to calculate something along the way here, you should be using the first order sort of equations that go with it. Now, there are really 2 sort of graphs that are associated with first order. This one on the left here is the concentration versus time. And in a first order reaction, what we do see is at the start, we have a lot of reactants. As time goes on, we do see a decrease, obviously, in the amount of reactants that are occurring. More so, though, when we sort of talk about first order reactions and the graph that's associated with it, it is actually this graph right here. The guy on the right is really the graph that we do associate with first order, and that is the natural log of A versus time. And the reason for that is we could use this equation right here, which is what is referred to sometimes as the integrated rate law, or the sort of concentration versus time one. That's the natural log of A is equal to the natural log of A naught minus KT. This A here is like the final concentration. The A with the naught is like the initial concentration. K is our rate constant. And T here is actually time, so not temperature. T here is time in that particular case. If you take this equation here and you rearrange it and write it as this, the natural log of A is equal to minus KT plus the natural log of A naught. This relationship here with this law will give you a straight line. Y is equal to mx plus b. And if we look at what is graphed there on the bottom right, that is what we see on the y, the natural log of A. On the x, we see time. And we can see from this equation that if we took the slope of the straight line, which should give you a nice linear relationship, with the slope will equal negative of the rate constant. That line that we see in this picture, which is a straight line, when you actually get the value for the slope, will it be a positive or a negative number? It will be a negative, right? It's a negative line. That negative plus the negative that's in the negative k gives you a positive value for the rate constant. So here, that's how we get to a positive value for the rate constant. That's why the slope here is equal to negative k, and not just k. So in terms of graphs for first order, definitely this graph is really the one most people associated with, but the guy on the left there is also a first order graph. You do need to know a couple of things. We'll add to this. We'll see it in just a second. But there's also the half-life equation that is specific for first order. The half-life is the natural log of 2 divided by the rate constant. The half-life is pretty much what the name sounds like. It is the time it takes for half of whatever you started with, basically, to go away. So if you started with 10, after the first half-life, you'd be left with 5. After the second half-life, you'd be left with 2.5. After the third half-life, I need a calculator. But so far, you just keep dividing by 2 at that point. So there's a few things on this slide that's really important for you to know. Again, it's important to know the units associated with the rate constant. Important to know this integrated rate law that will allow you to figure out, if you know the initial concentration, how much time elapsed, you can figure out how much concentration you would have left. And also the half-life equation is really important, and the two graphs, but really the graph there on the right. Any questions on that there? Now, speaking of these two equations, the sort of half-life equation and the integrated rate law there, the natural log of A is equal to the natural log of A naught minus KT. There are certain situations and some problems where you will need to use both of those equations together. And it would be a situation where perhaps they give you the half-life, but not the rate constant. So a lot of times you'll need to use the half-life equation to solve for K. And then you could actually go into the bottom equation there and you'll have K because you're kind of missing it. So there's sometimes in a lot of problems where you'll kind of use both of those equations together. And a lot of times if you're doing that, you'll be solving for K for the half-life equation and then sticking that K into the other equation to solve for what you're looking for. Any questions on that? Now, when we talk about sort of orders of reactions, first order, second order, zero order, these are very common sort of orders for reactions. And as you think about just most reactions you probably have seen, if you think about the number of reactants you got going on there, a lot of times, a lot of reactions may just have one reactant, right? Which would lead us to maybe like a first, zero, or second type order. Some will have two reactants, right? So if they're each kind of first order, it gets you to second order. Maybe one's, 0 and 2. A lot of times we don't really see reactions where there's like a lot of reactants, like 3, 4 reactants reacting at once. And that's why we really don't see a lot of really higher orders overall for reactions. We have like first, second, and 0 are very common. In theory, to get to like, third, fourth, fifth order and stuff, you need a lot of things kind of happening at once. And normal times those don't really happen with that many reactants. Here is again a plot of this reaction here. And again, you can kind of see we have like one reactant, natural log of the concentration of our reactant versus time. Again, if we take our slope of this line, that would get us our minus K. And that will obviously lead us to the rate constant. So let's try some here. We have a reaction that is first order, has a rate constant of 2.8 times 10 to the minus 2 reciprocal seconds. How long will it take for A to go from 0.88 to 0.14? So see what you come up with. Okay, let's take a look. So first off, a couple of things. they were nice enough to tell us that, this is a first order sort of reaction. If they did not, again, we could figure that out by looking at the units that we see on the rate constant there, and that will tell you that it is first order. That then should kind of point you in the direction to sort of our concentration versus time equation for first order, which is the natural log of A is equal to the natural log of A naught minus KT. If we think about some of the stuff that was given to us, we obviously have the rate constant given to us, 2.8 times 10 to the minus 2 reciprocal seconds. We have the initial concentration here of 0.88 molar, the final concentration being 0.14 molar. And pretty much that is everything that we need here. So putting it in, we go natural log of our final 0.14 equals the natural log of our initial 0.88 minus K times our temperature time. And I wanted to write that K there, huh? So let's put the K in there, which is 2.8 times 10 to the minus 2 reciprocal seconds times our time. We'll just go below. All right, at this point, if I'm going to do this on my calculator here, we're going to take the natural log, which is the ln button on your calculator, minus 0.14. I'm going to hit equals. I'm then going to basically subtract this guy to the other side. And I'm going to minus it from the natural log of 0.88. And if you do that, you end up with a negative 1.838279 is equal to our 2.8 times 10 to the minus 2 reciprocal seconds times time. And let me make sure I punch that in right. That seems maybe like it is. Yes. That's right. And that's negative there. There you go. And we're then going to take that number and divide it by our rate constant, which obviously has the negative on that side. So taking 1.838279, that's negative, divided by negative 2.8 to the minus 2, lays us up a time that is equal to 66 seconds approximately. Yes. Any questions on the math there? So in this case, 66 seconds, just about a minute it takes for the concentration of this reaction to drop basically from 0.8 to 0.1. That's pretty quick. It drops pretty fast, yes. Any questions on any of that there? Okay. Now, as I mentioned earlier, there is a specific half-life equation that does go for first order, and it is the natural log of 2 divided by the rate constant. If you put the natural log of 2 on your calculator, you'll sometimes see it just written as 0.693, which again is what you get when you take the natural log of 2 on your calculator. By the way, if you ever can't remember, I guess, the half-life equation, but you're able to remember, obviously, this equation, you essentially can substitute in initial divided by 2 for this guy and solve for t, and that will get you to the half-life equation. My guess, if you can remember that big equation, you probably can remember the small equation there. All right, so we want to know what is the half-life here of N2O5 if it decomposes at a rate constant of 5.7 times 10 to the minus 4. So again, in this particular case, since they were nice enough to give us the rate constant, we pretty much could go right into our half-life equation. Again, if they did not tell you that it was first order, we would know by looking at the units here that it is first order because of the reciprocal seconds. So the half-life in this case would be the natural log of 2 divided by 5.7 times 10 to the minus 4 reciprocal seconds. And in this particular case, we will end up with, looks like, about 1,216 seconds. If we're kind of significant figuring here, maybe about 1,200 seconds on the round there, since our original number had 2 significant figures in this case. Any questions on that there? Approximately 20 minutes. So again, you do obviously need to know these equations, know how to properly solve them. They are the equations, again, that we use specifically for first order reactions and specifically to help us figure out things like these questions, how long will it take for the concentration to change? Or if you let this guy go for so much time, how much will you have left over? Or after a certain period of time, how much did you start with? So those are all things that you will need to be able to solve for. So the half-life, as I talked about, is the time it takes for half of whatever you started with to really sort of go away. And that's what we see here, obviously, as we go from the first box to the second box, lose half the circles, half circles, half the circles. Approximately about after 10 half-lives or so, it's pretty much gone at that point. You don't have very much left. As we'll talk about in later chapters, things like radioactive decay and all nuclear radioactive decay follows first order kinetics. So it follows sort of this half-life sort of plan. All right, so why don't you give this one a go? We got this reaction as first order. We got a rate constant of 2.9 times 10 to the minus 4. Find the concentration at 865 seconds if the initial concentration is 0.0225. Take a few minutes, see what you come up with. Take a look. So again, if they weren't nice enough to tell you that, which they often are not, they can say that it is, again, first order here because of the rate constant units. That, again, will take us to our kind of time versus concentration equation here. In this particular case, again, we are given the rate constant. In this case, we are also given the initial concentration. We're looking for the final. And we're also given our time here of 865 seconds. So really, in this case, we have everything that we need on the right-hand side. So we're going to go natural log of A equals the natural log of our initial, which was 0.0225 minus our rate constant of 2.9 times 10 to the minus 4 reciprocal seconds, and our time, which in this case is 865 seconds. Now, something that you should note is you always want to be careful in this part of the place right here. It's a very common thing that sometimes the time's given to you in different units than the rate constant. So because the rate constant really has a unit of time, you want to make sure that both of those guys are always the same units. And a lot of times they may be different. And if obviously they are different, you got to get them into the same units. That means we could pretty much clean up what's on the right-hand side there. So you can do a little natural log of 0.0225. We're going to subtract it from 2.9. Make sure you use your exponent button, -4 times 865. That's going to give us the natural log of A is going to equal minus 4.0450997. I feel like writing numbers. To get rid of the natural log on the left-hand side, we need to take we got to go take that of both sides, basically, right? When we do it over here, this just becomes A, right? And then we end up with something like 0.0175. This would need a molarity as it is a concentration. We could kind of check ourselves. This definitely should be less than what we started with. So at least that's good. So, obviously if you ended up with more, something probably went wrong at that point. Any questions on that? By the way, the E button there is above the natural log. Yeah, on most people's calculators. So that is where you find it. Some have a dedicated button, but most are right above that one. Any questions on that particular one there? All right, so here molecular iodine dissociates at 625 Kelvin. with a rate constant of 0.271. What is the half-life? Okay, so this is first order. So again, we want to make sure we use our specific half-life equation for first order, which is the natural log of 2 divided by k, which is 0.693 really divided by k. In this case, they did just give us the half-life or the rate constant, so we can put it in. Gives us 0.271 reciprocal seconds. And looks like perhaps we end up with 2.6 seconds in this case. Again, obviously, when we do the division here, seconds come up on top. And that is a super fast reaction. Yes, so every 3 seconds, you lose half of what you started with, basically. Yeah. Any questions on first order and the equations that go with it? Okay. So the next type of sort of overall order we're going to talk about is actually second order reactions. And second order reactions are a little bit different in terms of some of the formulas. So first off, obviously, there's, again, a couple of different ways you could get to an overall second order reaction. Probably the most common way would be 2 reactions where they're both first order, right? Would give you to second order. You also could, again, have 2 reactions where one is second order, one zero order would get you there as well. If we sort of write a rate law here for a second order reaction, assuming that A is second order here, and we rearrange it and solve for K, here we see some different units associated with the rate constant for a second order reaction, some of which we saw earlier when we did some of the problems. It is 1 over molar seconds. Again, same idea here. The seconds doesn't necessarily always has to be seconds, the time part of it, but it is a very common one. So again, you could have 1 over molar minutes or 1 over molar hours. It's basically the same thing. But 1 over molar seconds, just like for first order, which is 1 over seconds, you need to be able to recognize that as being second order and make sure that you use the appropriate equations for it. The appropriate equations for sort of concentration versus time is 1 over A is equal to 1 over A naught plus KT here. All the characters here are basically the same thing. The A is the final, the A naught is the initial, the K is our rate constant, and the T is our time. As you can see, different than the half-life equation for first order, we actually have a half-life equation as 1 over the rate constant times the initial concentration. So unlike a first order reaction, in a second order reaction, the half-life is dependent on the initial concentration as to what is going to happen in that particular case. And obviously, if you have a larger initial concentration, right, that's going to affect the half-life than if you had a smaller one. So if you just want to visually sort of figure that out, you could just take 1 over 20, for example. And if we take 1 over 20, we end up with 0.05 versus 1 over, say, 200, right? 1 divided by 200 gets us 0.005, right? So smaller the concentration, right? Half-life is shorter. And this one is a lot faster, right? It happens a lot quicker in terms of time if you just do that. So it is dependent on the initial concentration. If we take the equation here and rearrange it and rewrite it as 1 over A is equal to KT plus 1 over A naught, that is our Y is equal to MX plus B. And that is what we see a typical graph for second order. On the Y is 1 over the concentration. On the X is still T here. And different though, we actually get a positive line here, right? So we get a positive slope and the rate constant will equal the actual value of the slope. So graphically here, you could do this graph. You could take the slope of it and you could determine graphically the rate constant, just like you could graphically determine the rate constant there for first order as well. So kind of the same information here off of this table is important. Units associated with second order, concentration versus time equation, half-life equation, and the graph that is associated with second order. Any questions on that? Again, a very common kind of reaction, since two reactants are very common, a lot of reactions to occur. I'm going to say yes and no. Yes, I don't know if I would ask you to graph it like on an exam, but you may be given a graph and need to kind of get the information from it. Yes, in the sense in lab, you'll do an experiment coming up where you'll do all these graphs for a bunch of different ones. And so, and in lab, we will do these type of graphs to help us determine what the overall order of the reaction is. In more of a lecture application or exam or quiz, you may be provided a graph with some information that you may need to pull off the information from. Yeah. In a homework problem, you may have to actually graph some of it. Yeah. So by the way, some of the homework problems out of like this first chapter, you know, sometimes the best way to sort of answer them is you have to open up or use something like Excel, make a graph, and, you know, kind of get the information that way on some of the homework problems that you come across, especially in kinetics. Other questions on that? Okay. The last sort of common type of order reaction that we do come across is a zero order reaction. And a zero order reaction, again, basically could be achieved by having a reactant that obviously is to the zero order. And that would give us basically a rate law that is equal to K times A to the zero. And as we've talked about, A to the zero would be equal to 1, which means essentially the specific units associated with a zero order reaction are really the same units that we see for the rate, which is molarity over seconds. So at this point, the three major sort of orders for reactions, they all have individual different sort of units associated with the rate constant. And like I said, there are a lot of problems you'll come across where they definitely will not tell you the order, but they will provide you that rate constant with the units. So you got to be able to recognize those. We have a sort of concentration versus time or integrated rate law that looks very similar to first order without the natural log part of it. So this is the concentration is equal to the initial concentration minus KT. Also has a half-life equation that is the initial concentration divided by 2K. So here again, the initial concentration obviously does play a role, and the larger the concentration here, we would probably end up with a larger number, right, for the half-life. And obviously the smaller concentration, since the initial concentration is up on top, we would end up with a smaller number. So the smaller number would result in a much quicker, again, half-life than the larger number here. Again, taking kind of like we did with all the other ones there, our concentration versus time equation and rearranging it properly here. Let's try that one more time. There we go, minus KT plus A over not there. That is going to be our Y is equal to MX plus B. And again, that gives us our typical graph, the concentration versus time, which will yield us a straight line where the slope is equal to negative K. Now you might recognize this graph. We saw this graph where else? Concentration versus time. We saw it with first order, but it did not look the same. So if you do a concentration versus time and you get a linear relationship like what we see here, it's a zero order, right? If you do concentration versus time and you don't get that linear relationship, kind of that decreasing with time, that is first order. Yeah. So even though they are graphing the same thing on those graphs, the result of the graph is different. A linear relationship should be achieved if it is a zero order when you do concentration versus time. Question on that? And as you probably can imagine, what I'm going to say right now is the exact same things. You need to know the units, you need to know this equation, half-life, and obviously the appropriate graph that goes with it. Any questions on those? Like I said, these are the typical sort of orders that we see. Again, to get sort of super larger orders overall, again, you need a lot of guys sort of reacting. And again, most reactions, like we talked about, you know, do pretty much have like one reactant or two reactants. 3 reactants sometimes is like really a lot, you know, so we don't usually go over more 3 reactants. So, you know, we typically get these orders. Are the other ones theoretically possible? Yes. And, you know, you could calculate some of those things, but most commonly, these are the 3 that we see. Any questions on that there? Okay. So let's give this one a go. This reaction is second order, initial concentration is 0.01. And after about 500 seconds, it is 0.001. What is the rate constant in this? Okay, so again, second order. So definitely want to make sure we're using the correct law here. So it's 1 over A equals 1 over A naught plus KT. In this case, we're given pretty much everything but the rate constant, which is what we're looking for. So our final concentration here is 1 over 0.0010. Our initial concentration there is 0.010. And our K we're looking for, and our time here is basically 500 seconds. At this point, I'm going to take 1 over 0.001, and then I'm going to subtract 1 divided by 0.01 from it. And if you do all that, so again, I basically did the guy on the left and then subtracted this guy to the other side, gets you 900 over there is equal to K times 500, basically. This basically would be 1 over molar seconds, or 1 over molar here. We're going to divide this to the other side. And when we divide that, we end up with 1.81 over molar seconds. Again, obviously, when we did the subtraction up here, 1 over molarity, when we divided, that brought our S to the bottom to the other side. It gives us the correct units that we associate, right, with a second order, which is 1 over molar seconds. Any questions on that there? So again, a reminder, you do need to know these equations. They will not be provided for you, so make sure that you do know them. Yeah. All right. Here's just a summary, get a little table, summary of all the equations and stuff that you need to know, obviously, along with the graphs that we talked about. And again, you can, and as we will do, like I said, in like 2 experiments from now, you can do these graphs. So if you ran an experiment and you really were not sure what the overall order was, you could take the information from the experiment and basically, you know, graph the concentration versus time, natural log versus time, 1 over the concentration versus time, and whichever one that would be the most linear. When you do something like the R-squared value, the one closest to 1 would tell you the actual order of the reaction based on that information. Any questions on any of that there? Okay. Then let's talk a little about energy and some reactions. So these are energy diagrams, which you might be familiar with. Energy diagrams, you know, really display sort of what is going on in a particular chemical reaction. When a chemical reaction takes place, again, there really is a couple of things that really does have to take place. We do need collisions to occur. So obviously the reacting molecules need to come in contact with each other. They actually need to come in contact with each other sort of in the correct orientation, the correct location, like the active side, if you will. And they also need to come in contact with each other with the right amount of energy, basically to kind of kick off that reaction, to get the bonds to start breaking and new bonds to start making. And when we look at these energy diagrams, the guy on the left there is exothermic. And when we talk about exothermic reactions and energy, we oftentimes talk about delta H, which is the enthalpy. And the enthalpy will be positive or negative for an exothermic. It'll be negative, yes. So negative for an exothermic reaction when you have a delta H value, positive over here, right, for a endothermic reaction. The reason the guy on the left is an exothermic reaction is when we look at our reactants, they are higher in energy than our products. So the only way to get down in terms of energy is for energy to be given off, right, or released. And that is what an exothermic reaction means, right? And heat and energy is being released as a result of the reaction. Opposite is true when we look at the endothermic curve. The reactants are lower in energy than our products. The only way to kind of get everybody up there in terms of energy is energy needs to be absorbed, right? which is basically the definition there, right, of endothermic. Now, when we start to have a reaction take place, basically what needs to happen is all these guys here, which are reactants, they need to start breaking bonds. And that is what happens as they start coming up this hill. You start getting some bonds breaking, but you also get some new bonds being made. A result of a chemical reaction, right, is nothing else happens other than we break a bunch of bonds and we make a bunch of new bonds, right? And everybody reassembles. We have the conservation of all the elements involved, right? That's why we balance equations. We start with 4 carbons, end with 4 carbons. They may be in different compounds or molecules at that point, but we have that conservation of energy or of elements because all we are doing is breaking basically bonds, which are electrons. So as this guy kind of comes up this hill to sort of the peak of the hill, we got this guy that's breaking bonds, starting to make bonds. And when we get all the way up to the very, very top here, at sort of the peak of energy, that is what is sometimes referred to as the transition state. The transition state is at the very top of the hill there, which is the highest in energy. And when things are high in energy, like in chemistry, is that like a really stable situation or not so stable? It's really not stable, right? Things don't want to be in really high energy. Things tend to want to be in lower energy, which is why a lot of times bond reactions occur. It kind of brings everybody down to a nicer state of energy. And what we get at the very top is this guy right here. This is what is sometimes referred to as the activated complex or the transition state complex. And it is a guy that basically has some partially broken bonds, some partially made bonds, which is why it's very high in energy. It's really hence in a transition state as it gets up there. And very quickly, it will sort of slide down the back end of the hill there and, you know, head towards the products. And that's why a lot of times in a lot of reactions, those sort of transition state complexes or activated complexes up on top are very hard to isolate because they don't hang around a very long time. They kind of get there and go, this is not a great situation. I want to kind of finish it up, and they drop down to their side. Now, speaking of this hill that they are climbing to get to the top, this hill is what is referred to as the activation energy. This hill right here, that is the E of A, which is the activation energy. And that is the minimum amount of energy that's really required for a reaction to take place. So when we talk about when they collide, they need that minimum amount of energy for the reaction to take place. It's that energy to get them up and over the hill to the other side. How does that affect the rate? Well, if there's only a small proportion of molecules that have enough energy to do that, the reaction should probably proceed very slow, right? There's a lot of guys that have enough energy to get up and over to the other side, right? We would expect the reaction rate to occur a lot faster. We see a very similar thing over here in our endothermic reaction, except that our hill here is typically larger or smaller than exothermic. It is larger, which also makes sense. This is endothermic, got to kind of help everybody up the hill, put some energy in there to get everybody enough energy to get everybody kind of up and over the hill. So we typically do see a kind of larger activation energy in endothermic versus exothermic a lot of the times because of it kind of net needs energy to be put in. So obviously the hill that everybody has to climb, that activation energy has a really big effect on the rate of the reaction. Clearly, the larger the hill, the longer or the slower the reaction will take place. Like if you were walking a giant hill, it's going to take you a lot longer to get to the other side, right? Than if you had just a very small hill to sort of climb. So endothermic, big hill, exothermic, still a hill, both have an effect on the overall rate of a reaction. Any questions on that there? So let's talk about the effect of temperature on the rate of the reaction. Changing the temperature changes the rate constant and the rate law. And there's actually an equation that relates it that we're going to to look at, and that's one version of the equation, which we don't use all that often, but we'll see a much nicer version in just a second. But this also explains why when we increase the temperature, right, we do see that the reaction rate will actually start to increase as well. And that is because when we increase the temperature, we're essentially putting what into the reaction? We're putting energy in, right? So that's going to give a greater proportion of molecules enough energy to hop up and over the hill to the other side. We can look at this equation here. T is the temperature in Kelvin. R is the gas constant. It's actually the gas constant that involves energy, the 8.314 joules per Kelvin per mole. A is the frequency factor, as we'll talk about in just a second, but the frequency factor basically is the proportion of molecules that do have enough energy to kind of get up and over to the other side. The activation energy, again, is the hill that you have to climb to get to the other side. And again, that minimum amount of energy that is needed to get there. So let's take a look at some of these things. As I mentioned before, you know, that is sort of the barrier that we go to the other side, is that activation energy. And as I mentioned, at the very top of that hill is where we do see that activated complex or the transition state complex. And it really is high in energy because it is in that transition state where we have the making and breaking of bonds sort of happening simultaneously. And it's, again, as we mentioned, very, very high in energy. Here's an example, again, of just a rearrangement, for example, here of where nitrogen and carbon are really just switching sides. As this guy goes through, we start to get, in this process, you can kind of vision it sort of coming up the hill here. As it starts to do so, we start to get the bonds starting to weak, and we start to get this guy to kind of rotate so it can start to make the new bond. So it's, as it's going up that hill to the transition state, is starting to move around and do that. And as you can see, as it approaches there, we do get this sort of transition state complex here where we got that partially broken bonds. We're getting some of this rotation to occur, and then eventually it will re-rotate to the proper positioning at the end. The difference in the reactants where they start and the products where they finish is the delta H for the reaction, right? And in this case, just looking at this, we would expect the delta H here to be negative, as our reactants, again, are higher in energy than our products in this particular case. So a more sort of useful way that we do use this equation is we can go through and take like the natural log of it. And if we take the natural log of this equation, we get this guy on the bottom, which is one that we see a lot. People still use this one, but a lot of people will use sort of this version of it. And it really is the same equation, other than we just went through and took the natural log of everybody. And what we do see is a couple of things. First off, this is a graph on the left of the rate constant versus temperature. And we can see at lower temperatures, right, we have a smaller rate constant, right? So low temp, small rate constant. Obviously, as we increase the temperature, giving everybody more energy, more proportion of guys that have enough to get to the other side, we have at higher temperatures a larger rate constant. This equation here is actually written in the form of a straight line on the bottom there. So if we take our equation like it's written there, this would be y is equal to mx plus b. So this is a very common version of this equation that we use for sort of graphical purposes to figure out things like activation energy and stuff like that, which means if I were to do this graph, it should yield me a straight line, right? And on the y, I should graph the natural log of k. On the x, I should graph 1 over the temperature in Kelvin. And that would yield me a straight line where the slope is equal to the activation energy over R, or negative the activation energy over R. So graphically, this is a very convenient way that we could graphically determine the activation energy for a reaction if you have the rate constants and the different temperatures. Clearly the temperature here does need to be in Kelvin, yes? So absolute temperature is still Kelvin here, much like most things in chemistry. Pretty safe bet that this temperature should be Kelvin. So here's a typical sort of graph of what one of these Arrhenius plots look like. This is an Arrhenius equation, by the way, and this is what is sometimes referred to as the Arrhenius plot. And it's the natural log of K versus 1 over the temperature in Kelvin. Here, we would take this slope of this line, it would equal minus E of A over R, which is really convenient because from the graph, we would have the slope, and R is that gas constant, 8.314 joules per Kelvin per mole. So, but just by very simply rearranging this equation, we could solve for the actual activation energy. Couple of things, the activation energy on both of those sort of graphs that we saw a second ago there were these, right? Activation energy, should it be a positive number or a negative number? It should be a positive, right? In both graphs, you had to put the energy in to get up there, right? So it should be a positive number. And that's why when we look at this graph, this line should yield us a negative slope, right? Along with the important negative sign that's here, right? Should turn our activation energy into a positive number when we solve for it. So you, for pretty much most cases, should end up with a positive number for the activation energy. The other important thing is when I do solve for this, what would my units be for the activation energy? What would my energy units be here? It would be joules, yeah. So it would be joules per mole, yeah. Kelvin would cancel out here, yeah. And you would, but most importantly, you will get joules. Very often, though, activation energy is given in kilojoules. So sometimes people will take it off the graph and think it's the kilojoules, but it is the joules, and 1,000 joules in a kilojoule, right? So you need to do that conversion sometimes a lot. The other thing you have to watch out for is maybe if you're just mathematically doing, which we'll talk about in a second, if you are given the activation energy, it will typically be in kilojoules and our R is in joules. So you want to watch out for those differences in units so you're not off by a factor of 1,000, you know, when you do put those things in. All right, so a couple of things here, some of the stuff we talked about. Again, that sort of frequency factor, or that A, really is sort of that proportion of molecules that really do have enough energy to get up and over to the other side. That's why, as we just talked about, when we increase the temperature, it gives a greater proportion of guys enough energy to get to their side. The end result of that is we should see an increase in the rate constant, the rate of the reaction. Vice versa, we could do the opposite, right? We could take everything and throw it on ice, right? If we put all our test tubes on ice before we did the reaction, that would be essentially like removing energy from that reaction. And the opposite would be true, right? We're now going to have a smaller proportion of molecules that have enough energy to get up and over to the other side. The result of that is the overall rate should go down, right? It should decrease. We also would probably see a decrease in the rate constant as well because of that. Any questions on any of that there? All right. And that's what we see in this graph here. We're at 2 different temperatures, but temperature 2 here is a higher temperature. And what we see is in terms of temperature 2, which is the higher temperature, this amount of molecules basically have enough energy basically to get to the other side. When we look at the lower temperature there, it's basically only like this amount of guys that have enough energy basically to get to the other side. So you can see definitely by increasing the temperature, a greater proportion of molecules are able to achieve that activation energy and get to the other side at the higher temperature versus the lower temperature. So as I mentioned, we use this guy really to do a straight line plot, an Arrhenius plot. And let's take a look at a problem where we would do this. So clearly, you may again come across a problem like this in homework where you might want to lay up an Excel graph or some type of spreadsheet type graph to do this. So this is typically what we're given. In a lot of cases, you may actually be given the temperature in degrees Celsius instead of Kelvin. And we go from Celsius to Kelvin by adding 273. That's good, right? So a lot of times you will give a table like this and it's actually in Celsius, because obviously on our thermometers, we usually will get like Celsius. So if you happen to give it in Celsius, you would need to go through and convert them all to Kelvin, obviously, before you did this. Once we now have them in Kelvin and we have the rate constants given to us, we would then need to take all these temperatures and do 1 over the temperature, right? And that is really what we should be plotting. We would need to take all the rate constant values and take the natural log of the rate constant. And that again is essentially what we should be plotting, the natural log of all those values on the Y, the 1 over temperature in Kelvin on the X. And if we did that in Excel or something like that, we would get a nice, very nice looking graph here where it's very linear. And we would obviously want to get the equation from this graph. And from the equation from this graph, it will allow us to calculate a couple of things that it did ask for, which is what is the activation energy and what is the frequency factor, right? And again, if we look back here, this equation here is our Y is equal to our mx plus b. So the slope of the line is going to equal minus E of A over R, like we talked about. So in this particular case, the slope will equal minus E of A over R. The importance here is we can again see that our slope is negative, so we want to make sure we keep that negative. That would give us negative 1.12 times 10 to the 4 is equal to minus E of A divided by 8.314 joules per Kelvin per mole. At this point, we basically would multiply the 8.314 to the other side. And that would give us an activation energy here. If I punch it in correctly, it'll give me the activation energy, right? All right, I'll try that again. 1.12 exponent 4, right? Gives me 93116.8. Really, in terms of units, Kelvin's there, so Kelvin cancel. This would be like joules per mole. If we wanted in kilojoules, that would be something in the ballpark of 93.1 kilojoules per mole would be our activation energy. Is a positive number, as we talked about there, again, because of the negative here and the negative here turns our activation energy into a positive number. Any questions on that calculation? We could also calculate the frequency factor from this. And again, the frequency factor is A in this equation. And that is equal to basically the y-intercept. So the natural log of A is equal to the y-intercept. So we would do the natural log of A equals the y-intercept. This is our y-intercept in this case, right? And in this case, that would be, excuse me, the natural log of A equals 26.8, just like we did before. We want to take the E of both sides, right? And when we take the E of both sides, that will give us that A is equal to, in this case, 26.8, gonna give us, I'll come down here, 4.36 times 10 to the 11. Now the question is, what are the units associated with the frequency factor? So if we go back to our table here, these are the units of the rate constant, right? When we take the natural log of K, in this case, the units actually go away. Yeah, so there's like no units on the natural log of K. But at the end part of our calculation, we did basically the E of that, right? So we kind of just threw the units back. So the units typically will end up the exact same units as what the rate constant units were. So in this case, the rate constant units, which is reciprocal molar seconds, would be our units. And that's because, again, the units for the rate constant kind of go away when you do this, but then we did the E. So we then kind of put them back together in terms of the units, and they come back to be in the same units that we see for the rate constant. Any questions on graphically here, how you would do this? Again, in lab, you will do this with the numbers and stuff. Again, in lecture here, the graph may be provided for you with the equation. Again, you need to know how to obviously pull off the information to solve for something like activation energy or frequency factor. Any questions on that there? Yeah.
What you just solved today was just finding the rate constant from this graph.
So according to the equation from which the graph was made, which is this equation here, right? Right underneath. So really the graph that we just looked at comes from really this equation. And that is, again, y is equal to mx plus b, which means what we graphed was a natural log of k, and on the x was the 1 over t. And from this equation, the relationship to that line is basically the y-intercept, which is b, where the line will cross the y, is actually equal to the natural log of the frequency factor. And so when we solve for it based on the equation, the line, that's how we get to the frequency factor from there. And in terms of the units, what I was talking about was the kind of the units of it. So when we go to graph it, the units end up being really the same as the units associated with k in that case. Other questions on that? And the reason for we're looking at k is because it's really the y-intercept. So when the line goes across, it crosses really here, the y-axis. So that's why we're looking at the units associated with that. Yeah. Other questions on that? Okay. So that is the graphical way that we could solve these, and really, who's going to make graphs all the time? So there is actually sort of a 2-point version of it where technically if you got like 2 points along that line, you could mathematically solve for it. So this is an equation, and depending on your book and where you look at, you may see some different versions of this equation, but we'll go with this equation since it's in front of us. But sometimes you will see like on this side of it, like the negative distributed out with the E of A, and it's like 1 over T2 minus 1 over T1. Sometimes you'll see like in the parentheses, like all the temperatures combined, like, T1 minus T2 divided by T1 times T2. So there's a few different versions of this equation. I would perhaps pick one and stick with it. So we'll go with this one. These are pretty much our normal things here. K2 and K1 are 2 different rate constants at 2 different temperatures. And obviously T1 and T2 are the 2 temperatures that go with the rate constant. So really important to make sure that you keep obviously the rate constant and the temperature, whichever one you want to call 1, whichever one you want to call 2 in a problem. It really doesn't matter as long as you keep those 2 guys together as either the 1s or the 2s in that problem. The E of A is our activation energy, and the R again here is our gas constant, which is still that 8.314 joules per Kelvin per mole. And this is really the version of this equation where you really do got to be super careful here. Again, that is typically going to be given to you in kilojoules. So you're going to have that differences in those units. So you want to make sure that they are in the same unit. It's a very common mistake that people will kind of leave 1 in kilojoules and 1 in joules and find themselves sort of off by that factor. Obviously, in this case, you just need 2 points to do it without the graph. So why don't we try it and see how our math does? We have a rate constant of 2.57 at 701 Kelvin, 567 at 895. What is the activation energy? Okay, let's take a look here. So obviously we got a couple points, so we could use the non-graphical version. So that's the natural log of K2 divided by K1 equals E of A, no negative, E of A over R, 1 over T1 minus 1 over T2. In this case, we're already in Kelvin, so we're good. We don't have to do that conversion. We basically just need to plug in here. So it's going to be the natural log. I'm just going to go with the first one in the problem as the 1s and the second ones as the 2s. So in that case, if I did that, the 567 would be 2 for me. The 1 would be 257. We're looking for the activation energy. Obviously, our R is 8.314 joules per Kelvin per mole. Let's speak correctly here. Since I did that, that means my first temperature there would be the 701 minus my second temperature would be the 895. So I can clean up the left-hand side. Again, a very common mistake people make as well is you need to divide first and then take the natural log of it. Yes. So if you do that, you get like a 5.39645 if I don't do anything with it. E of A over 8.314. And I'm going to also clean up what's in the parentheses on the right-hand side there. So that's 1 divided by 701 minus 1 divided by 895. Looks like inside the parentheses here, 0.000309215. At this point, mathematically, I need to multiply, right, the 8.314 to the other side, and then come back and divide by that number in parentheses. So 5.396453 times 8.314 gives us about a 44.8661 equals E of A. That's now going to be times this number, which then needs to be divided to the other side. And if we do that, we end up with an E of A of 145,096.8. The units there would be joules. Since we're looking for kilojoules, we're going to move it in about 3 places or divide by 1,000. Gets us about a 145 kilojoules per mole. Yeah. Again, we yielded a positive activation energy, which is good. Any questions on the map there? So this is probably the equation that we would use a lot for obviously the Arrhenius equation and finding the activation energy or the temperature. Obviously, it's not just solving for activation energy using this equation. You could solve for the value of a rate constant at a specific temperature if you didn't know it, but knew everything else. You could also solve for obviously a temperature as well. So you need to be able to solve for obviously anything within this equation along the way. Any questions on any of that? Yeah. Because they wanted it in kilojoules. Yeah, so when we did solve here, it was in joules. So divided by 1,000, or you can move it 3 places to the left. We'll do that for you. Other questions? All right, it's a good place. We will lay it up here today.